at Stanford University.
All right, last time we worked out basic Lorentz transformations relating two frames of reference. Whether or not I said it, let me say it now. We were mainly dealing with problems in which all of the motion, and in particular the relative motion of different observers, is along one particular axis. We didn't try to think fully three-dimensionally. And the picture you could have in your head is that we have a long railroad track, one-dimensional. Some set of observers is sitting still at the station. We could call those the stationary observers. And other observers are in the train, and they're moving relative to each other along the one-dimensional axis. And we didn't worry very much about the other axes. I said one or two things about it. And we talked about how you relate the coordinates of one observer relative to the other. And in particular, we wrote down Lorentz transformations based on the basic hypothesis of Einstein that all reference frames see the speed of light exactly the same. In fact, we said with the units that we used, all observers see the speed of light being 1. That's, of course, a choice of units. We work in years and light years, or seconds and light seconds, whatever choice of units. If we choose them correctly, we can make the speed of light 1. And that simplifies equations. Of course, if we really want to plug in to the real observational physics, we might want to use the fact that the speed of light in common units, in the common units that an experimental physicist would ordinarily use, is not 1. It's 3 times 10 to the 8th in some units. And so we would put back the speed of light. And there's always a unique way to do that. The unique way to do it is to make sure, simply stated, that you modify the equations by appropriate factors of the speed of light, c, so that the equations are dimensionally consistent. I will go back and forth. Mostly I will use the speed of light set equal to 1, but every now and then, just to illustrate a point, I will stick the speeds of light in, and you can go through the equations and do that yourselves. Okay, so two observers, one moving down the axis with a velocity v relative to the stationary, moving down the tracks with velocity v relative to the stationary observer. Stationary observer sees the moving observer moving v units of space per unit time, v being velocity. And of course, by symmetry, just by the symmetry of the problem, if we believe that all coordinate frames are equally valid, the same relationships, the same kind of Lorentz transformations, will relate the stationary observer's coordinates to the moving coordinates. It's a two-way street. The stationary observer ascribes stationary coordinates, the moving observer ascribes his coordinates, and they can each be related to each other reciprocally. And the reciprocal relation is truly reciprocal, exactly the same relations, except that whereas if I were moving to the right, your right, if I were moving to your right, you would say my velocity is positive. You would be moving to the left. As far as I was concerned, I would say your velocity was negative. And so in relating the two frames of reference, the only thing we have to remember is there's a sign change of velocity when you go back and forth. Okay, so for example, if x prime is the coordinates as seen in the train, here's the train over here, let's draw a train. That's the train. Okay, there's an observer in the train, and there's an observer in the tracks, or an observer in the station. Here's the observer in the station. Here's the observer in the train. And the observer in the train is moving with velocity v. The observer in the train has meter sticks, and the meter sticks can be laid out on the floor here to form a grid. The observer also has a timepiece, a clock. Likewise, the observer at rest, well, at rest with respect to whom? At rest with respect to the station. The observer at rest with respect to the station also has his meter sticks laid out and also has his timepiece. And they make various comparisons. You know how all of this works. An event which takes place. An event which takes place, an event means an event happening at a point of space and a point of time. In other words, at some point of space-time. I like to think of it as a flash bulb exploding someplace, going off someplace. It doesn't matter whether it's in the train or outside the train. Let's say in the train for convenience. A flash bulb goes off over here at a time that the stationary observer reckons to be t, time t, at position x. Now, position x means coordinate x in the stationary reference frame, x right over here, at a time t according to the timepiece of the stationary observer. So the stationary observer ascribes to it coordinates x and t, and the moving observer ascribes to the same event coordinates x prime and t prime. And we worked out the last time the relationships that are necessary between xt and x prime and t prime such that everybody will always agree that the speed of light is 1. Let me write them down quickly. X prime, these are the Lorentz transformations. X prime is equal to x minus vt. Now Newton would recognize that, but what he wouldn't have recognized was the square root of 1 minus v squared downstairs. And if you want to put back the speed of light, it goes right over here. I'm going to put it in and then take it out. V squared over c squared. And of course, if the velocity is small by comparison with the speed of light, this is a terribly tiny correction. Let's just call it 1 minus v squared. And t prime is equal to t minus vx divided by that same square root of 1 minus v squared. If we wanted to add the other two directions, in particular the directions out of the board and vertical, in other words, the directions perpendicular to the tracks, we could add them in very simply. Perpendicular directions don't change under a change of velocity along a given axis. If the velocities of the two frames, relative velocities, are along the x-axis, then the y and z coordinates are unchanged. Y prime equals y and z prime equals z. I won't write it. If we need it, we'll use it. We can invert these relations. This is simply a matter, there's nothing sophisticated going on here. This is simply a matter of solving for x and t in terms of x prime and t prime. Let me remind you what the result would be. It would be x equals x prime plus vt prime divided by that same square root, and t equals t prime plus v x prime divided by square root of 1 minus v squared. The only difference, the only asymmetry, is where you saw a velocity over here, you change the sign of the velocity just to account for the fact that the relative velocities are in opposite directions. You can also read off, if somebody gave you this form for the relationship between the coordinates, you could easily read off what the relative velocity between the two observers is. You look at the x equation here, and you say the moving observer's coordinate is x prime equals 0 right at the position of the origin of coordinates inside the train. x prime is equal to 0. X prime equals 0 corresponds to x equals vt. You just look at this and you say the moving observer, the prime observer, let's not call him moving, the prime observer is at rest, or the position x prime is at rest, or is equal to 0, excuse me, x prime is equal to 0, the origin of the prime coordinates corresponds to x equals vt. You don't have to know about this denominator there. You just look at x equals vt. That specifies x prime equals 0, and that tells you x equals vt, tells you that the relative velocity between the two of them is v. All right, now we want to do another exercise. The other exercise is to assume there's a third observer. The third observer is moving relative to the railroad car, relative to the train. He's got a little kiddie car inside the train. And he's moving relative to the passenger. Let's call him the passenger. He's moving relative to the passenger with velocity u. The passenger sees the little kiddie car, the little kid in the kiddie car, pedaling down the aisle of the train with velocity u relative to himself. Question: what does the stationary observer ascribe to the car? What velocity does the stationary observer see? And the way to solve this is just to use, I know of no way to guess the answer. The answer is some velocity. We can give it a name. We can call that velocity W. You could use V1, V2, and V3, but I hate subscripts. And so I prefer to say the velocity of the train is V relative to the stationary observer. The velocity of the car relative to the train is U. And the velocity of the car relative to the stationary observer I will call W. All right, so the stationary observer sees the car move with velocity W. And the question is, what is W in terms of U and V? And the answer is just to use a bit of logic. The bit of logic is that the relationship, first of all, we should give there are also coordinates, excuse me. There are also coordinates in the car, moving with the car. This could be a set of meter sticks laid out on the floor of the car, and also a timepiece that the driver of the car has. Okay? So there's three sets of coordinates. In this case, x and t are the coordinates that the stationary observer uses. X prime and t prime are the passenger's coordinates. And a third set of coordinates, which let's give them the name x double prime and t double prime. X double prime and t double prime are the coordinates that the kid in the kiddie car uses to describe things relative to the position, relative to his own frame of reference. All right, so now it just takes a little bit of logic to say we know what the relationship is between the double prime coordinates and the single prime coordinates. Those are related by velocity u. U is the velocity of the double primed relative to the prime coordinates. So we can write down those relationships straightforwardly. We don't need this over here. Let's write them down here. X double prime is equal, same exact kind of relationship. Same exact kind of thing, except we'll put in primes here. And instead of v, we will use the relative velocity u. All right, so this is going to be x prime minus u t prime divided by square root of 1 minus u squared. All right, so this is the Lorentz transformation between the double prime frame and the single prime frame. T prime minus u x prime over root of 1 minus u squared. All right, so now how do we find the connection between the double-primed coordinates in the car and the unprimed coordinates at rest in the railroad station. And that's simple. All we do is, let's take this equation over here. Let's focus on this one. The time equation also works out very nicely, but let's focus on the space equation here. We know what x prime is in terms of x and t, and we know what t prime is in terms of x and t. So all we have to do is to plug in. And let's do so. Oh, good. Nice, good pen. All right, so x prime is x minus vt divided by square root of 1 minus v squared. Now that's just this x prime here. So far that's just x prime minus u t prime, and let's put in t prime. T prime is t minus vx, and the whole thing again divided by another square root of 1 minus v squared. Now so far I have only written this and this. I have to put in the denominator. To put in the denominator, I just put in another factor of 1 minus u squared, 1 minus u squared, square root of 1 minus u squared. So that is the relationship between x double prime and x. We can write this a little more simply. Let's focus on what, there's some big denominator. The denominator involves the product of the two square roots. All right, let's put it in. Square root, square root. I'm not going to write out what's inside the square root. It's just the product of these two square roots. But I'm interested in the numerator, really. The numerator has an x, and it has a plus uvx. X here, and plus uvx. Why is it plus uvx? Because there's a minus sign here and a minus sign here. X times 1 plus uv. 1 plus uv x. And what about t? T will multiply minus v plus u times t. Minus v and minus u times t. And this is the answer, but it's not very transparent what it means. But all we need to do to figure out the relative velocity of the double prime frame relative to the unprimed frame is just to do exactly what we did over here. If we want to find out what x prime equals 0 means, just set x minus vt equal to 0. And that tells you that x is equal to vt. It tells you how the fellow at rest here, who is at x prime equals 0, how he's moving relative to the unprimed frame. So we do exactly the same thing. We say x double prime will be 0. X double prime, of course, being 0 means the position of the kid inside the kiddie car here. X double prime equals 0 is the same thing as the numerator here being 0. Denominator, who cares about the denominator? It's not, it's there, but we can set the numerator equal to 0 here, and that will tell us under what circumstances x double prime is equal to 0. So what does it say? It says x double prime is equal to 0 when 1 plus uv x is equal to u plus v t. I've set this equal to this to make the numerator 0. Or if I divide by 1 plus uv, it tells me x is equal to u plus v over 1 plus uv t. So what is the relative velocity? Sorry, yes, what is the relative velocity? This tells us the x and t trajectory of the kid in the kiddie car here. The trajectory of the child or whoever it is in the kiddie car is x is equal to u plus v over 1 plus uv times t. That corresponds to x double prime equals 0. All right, but another way to say it is just that the stationary observer sees the kitty car, the kitty car moving along with velocity u plus v over 1 plus uv. So we now know what w is. That's exactly what w is. W, we worked it out. We can write it in the form, well, let's write it in the form x double prime is equal to t minus wx divided by square root of 1 minus w squared, and t double prime is, did I write that right? No, I didn't. X minus wt. And t minus wx over the same square root. I don't have room for the square root there. All right. And what do we find w is? W is just this. That's how fast the kitty car is moving as seen from the stationary frame. So, yes?
Why is that dimensionally incorrect?
Because we set c equal to 1. Right. We're going to put them back. We're going to put them back in a minute. Yeah, we're going to put them back in a minute. Yeah, you're a step ahead of me. Okay. All right. So x is equal to, so w, the speed w is equal to u plus v divided by 1 plus uv. And now if I want to restore the units, just to answer your question again, if we set the speed of light equal to 1, of course, we're working in units in which velocities are dimensionless. But if we want to restore the dimensions, we simply look at this equation, we say, look, w equals u plus v, that's dimensionally fine. It's adding 1 to uv, which is peculiar, but we restore the dimensions by putting in c squared here. 1 plus uv over c squared, uv over c squared is dimensionless. All right, so this is the equation with c being restored. What is the Newtonian equation? The corresponding pre-Einsteinian equation? Well, stationary person sees passenger moving with velocity u. Passenger sees kitty car moving, stationary observer sees passenger moving with velocity v. Passenger sees kitty car moving velocity u. The answer naively would just be u plus v. But it's not u plus v. It's u plus v divided by something which, as long as u and v are significantly smaller than the speed of light, uv over c squared will be very small. We'll put in some numbers in a minute just to test it out. But as long as u and v are small compared with the speed of light, this will be negligible. It's the product of two ordinary velocities, 100 meters per second, or whatever it is you want to put in, divided by 3 times 10 to the 8th meters per second, all squared. This is a very, very small number, and it's a very small correction. On the other hand, when u and v get up near the speed of light, it can get very significant. So let's see what happens. First, let's do the case where u and v are small velocities compared to the speed of light. We can leave out... Well, remember that u and v mean velocities measured in units of the speed of light. Okay? So if u and v are measured in units of the speed of light, and let's say, for example, supposing u is equal to 0.01, 1% of the speed of light, and let's say v is also 0.01, they're both 1% the speed of light, then this turns out to be 0.02, that was what Newton would recognize, divided by 1 plus, and now uv is 0.0001. Did I do that right? Yeah. And 0.0001 is a very small correction. Now, this is a very sizable velocity, incidentally. U being 1% of the speed of light is damn fast. It's not 3 times 10 to the 8th, it's 3 times 10 to the 6th meters per second. So this is pretty fast, but the correction is small. 1 plus something. Notice the answer is a little bit smaller than what Newton would have estimated. This number here is a little bit bigger than 1, and so in the denominator it's a little bit smaller. All right, let's go to the other extreme. Let's suppose u and v are 90% of the speed of light. We could do 99%, but I'm not so good at arithmetic. U and V are 0.9. V equals 0.9. Newton would have said the kiddie car is moving faster than the speed of light relative to the stationary observer. In fact, he probably would have said 1.8 times the speed of light. He would have added these two numbers, but Einstein would have put in the denominator here, so let's see what we get. We get 0.9 plus 0.9, that's 1.8, divided by 0.9 squared. 0.9 squared is 1.81, slightly bigger than 1.8. The result is that the net velocity is slightly less than 1. In other words, we have not succeeded in making the kiddie car go faster than the speed of light, even though blah, blah, blah. You know the rest of the story. So this is the answer to the question, what happens if an observer is moving faster than the speed of light? Well, you could ask that question, but I think we are pretty well protected against people moving faster than the speed of light if the way they are made to move is relative to some previous frame of reference moving speed slower than the speed of light. In other words, there's no way by putting another observer inside the speed of car here, making him go 90% of the speed of light, et cetera, we're never going to get faster than the speed of light. So it's consistent to, it's a consistent thing to say all observers move slower than the speed of light, even though they can move arbitrarily close to the speed of light relative to each other in any combination, the net result will still be slower than the speed of light.
If U and V are C, then W ends up being 2 over C.
If U and V are C, that means 1. Okay? Let's suppose U and V are 1. C and 1 are the same thing. Then U plus V is 2, and 1 plus UV is 2. So the net result is the speed of light again. Okay? So if you're moving if each one is moving very, very close to the speed of light, the net result, in other words, if the kiddie car is moving relative to the passenger very close to the speed of light, and the passenger is moving relative to the station very close to the speed of light, the result will be that the kiddie car is moving relative to the station and even closer to the speed of light, but not in excess of it. Okay, that's the...
You see that through the stationary sees it through the eyes of the X prime. What if the train had glass walls and the stationer was looking at both of them?
If the train, I assume the train did have glass walls. I don't see how that makes any... We're not talking about how appearances look. We're talking about how measurements of phenomena by meter sticks and by well-designed clocks correlate with each other. What somebody sees is much more complicated for the simple reason that when an event happens, light has to come from the event, and it can be much more complicated what you visually see. We're not talking about what you visually see. We're talking about correlating the locations and times of events in frames of reference which are defined by meter sticks at rest relative to observers and timepieces which are also at rest relative to them. And it doesn't matter what kind of walls the car has, the transformation laws are universal. Okay. Now, the next thing we talked about last time was the notion of proper time or proper distance or proper interval. Let me just remind you quickly about that, very quickly. If we have an event taking place at point X and T, we found out last time that there's an invariant notion of separation, space-time difference, or space-time distance between them, proper time, and the proper time, or the proper, let's put this up higher. over here, xt. The proper interval between them is called tau, and it's defined by tau squared is equal to t squared minus x squared. And the interesting thing about this, the important thing about it, is it's the same in every reference frame. If the reference frame is moving, then we would use prime coordinates, but the same quantity here is t prime squared minus x prime squared. It's also equal to t double prime squared minus x double prime squared. It's an invariant. All observers agree on the value of this interval between here and here. They don't agree about the coordinates themselves, but they agree about this notion of proper time. The proper time is also the time read by a clock moving between these 2 points. If the clock is set equal to, let's say, 12 noon at this point, and it moves along this trajectory, then the time that it reads at the end of the trajectory is the proper time. And we worked out the time dilation last time. But what I did want to say about this, I want to now put back the other 2 coordinates, y and z. Y and z. And let's put them back into the game for a moment, or put them back in. There is another kind of transformation that we can do, not just a transformation between 2 moving coordinates moving along the x-axis, but we can also consider rotations of coordinates. Let's, for the moment, not even think very much about relativity. Let's just talk about 2 different coordinate systems related by an ordinary rotation with respect to each other. So the stationary observer might have 2 different coordinate systems, one oriented along the xy axis and another one oriented along some x prime y prime axis. Not the same primes. Some other set of axes, rotated or at an angle relative to the original ones. All right. What happens, now we can forget the prime coordinates for the moment. What about this x squared here? This x squared is really the distance from the place where the clock started to the place where it ended up in the unprimed coordinates. Now, supposing we take into account the other directions, let's call this y, for example, then this becomes a plane here. This point might not be located directly over the x-axis. It might be a point in space-time which is not at the same value of x as the origin here. What then is the interval between here and here? What is the invariant quantity? Well, this is actually fairly simple. As long as the event is located on the x-axis, it's t squared minus x squared. If it's not located on the x-axis and we make a rotation, then what was originally x squared becomes x squared plus y squared plus z squared, becomes the spatial distance between the origin and this point over here. This really becomes minus x squared minus y squared minus z squared. Etc. So if we're not working strictly along a one-dimensional axis, the invariant proper time between a start of a clock and the place where the clock gets to is given by t squared minus the square of the spatial distance, which is x squared. This is Pythagoras' theorem. It's just Pythagoras' theorem applied to x, y, and z. And that's the notion of proper interval. And that's the one we'll work with. If we make any combination of Lorentz transformations and rotations of coordinates, we will always find any 2 inertial frames which agree at this point over here, we will find out that tau squared is invariant. It's the same in all inertial reference frames. And it's very, very similar to the idea that, that in ordinary Euclidean geometry, different coordinate axes will ascribe different coordinates to a point in space, but they will always agree about the distance of a point from the origin. Here, it's this funny kind of distance with a relative different sign between the space components and the time components. And that is probably the most central fact about relativity, is that this combination is invariant. That's really what it's all about. Okay, so let's keep that idea in mind and introduce a little bit of notation. We get tired of writing x, y, and z, and we try to condense the notation. So let's condense the notation to standard relativistic notation. Yeah?
Just going back to the train there for a second.
Yeah.
If you assume that the speed v, let's say it was 0.9, like you said, it was very close to the speed of light, and the speed u, let's say that instead of a car, that guy has a flashlight in his hand, so he's actually sending a light beam, and that's...
Why don't you try it?
And I'm kind of wondering, like, how do these two people measure the speed of light, whether they get the same number?
Why don't you try it? Take one. Yep. Here it is. What if c is the speed of light? That means it's 1. Suppose v is 1. Oh, I don't know. Which one do you want to make 1?
Make u 1.
Make u 1. Okay. Make u 1. That's 1 plus v divided by u is 1, 1 plus v. So the answer is 1. The speed of light is the speed of light. That light ray moves with the speed of light.
In both frames.
In both frames.
Last week I was confused about something, and you pointed out that generally it comes down to simultaneity, definitions of simultaneity.
Yeah.
The question I asked a minute ago, I realized that with the glass walls, to try and look at both of them is trying to reintroduce simultaneity into the...
Okay, if you understand it, good. Yeah. Let's talk about light rays, how light rays move. Light rays, let's go back to the one-dimensional case then, one space and one time dimension. Let's go back. Light rays move, for example, along 45-degree axes like this. That means they will move from the origin to the point x, t, but only if x is equal to t. That's just saying the light moves with velocity 1. In a certain time t, the distance it moves is equal to that time, so it moves to the point tt, or the same coordinate. That means that t squared minus x squared is equal to 0, or that the space-time interval, I'll call it space-time interval, proper time, any number of different usages, is 0. That's different than ordinary Euclidean distance. Euclidean distance, if 2 points have genuinely 0 distance between them, they're sitting on top of each other. In space-time, if 2 points have space-time distance or proper time equal to 0 between them, that simply means they are related by the possibility of a light ray going from one to the other. Now, if we introduce the additional coordinates y squared and z squared, then what was originally x squared, the distance that the light beam traveled along the x-axis, the square of the distance, will obviously become x squared plus y squared plus z squared, square of the distance, and that will be equal to 0 for a light ray. So the motion of a light ray is t squared minus x squared minus y squared minus z squared equal to 0, or again, tau squared is equal to 0. Tau squared is... So that's one concept of how a light ray moves. It moves along trajectories such that the proper time along the trajectory is equal to 0. Photons move that way. We could draw a picture for this. A light ray moving to the right is a 45-degree axis to the right, 45-degree line to the right. A light ray moving to the left moves exactly the same way, except in the backward direction. What about a light ray moving outward? Well, that moves the same way, except at a 45-degree angle in the outward direction. More generally, we would draw a kind of cone. Now, I can't draw the full 3 dimensions plus time. That's too many dimensions for me to draw on the blackboard. But if we had only 2 dimensions, x squared plus y squared, instead of, let's forget the z squared here, we would find that the motion of light rays is such that in space-time they move along the cone created by 45-degree light rays coming out of the origin there. That's called a light cone. A light cone is the set of points that a light ray can arrive at if it starts at the origin. That's the notion of the light cone. And this would be called the future light cone. The future light cone is all of the places that light can get to starting at the origin. There's also a thing called the past light cone. The past light cone is all of the places that can send a light ray to the origin. So the future light cone is all the places that the origin can send a light ray to, and the past light cone is all of the places that can send a light ray to the origin. But they're just the cone turned over on its nose, the past light cone and the future light cone. And this is terminology. Terminology is often very helpful, but that's all it is terminology. Yeah.
You said the fundamental invariance for these systems is tau squared equals t squared minus x, y, and z squared. There must be something equivalent for Newtonian mechanics, some invariant. What would that be equivalent to?
Just t. Just t. Everybody agrees about the time interval between 2 events. The time interval is just t. Right? That's a good point. All right, we're getting close to... Let's talk about the concept of Fourvector. The most primitive, the most basic example of a vector in ordinary 3-dimensional space, and I am not talking about the kind of vectors we talked about last quarter. We're not talking about state vectors in quantum mechanics. We're talking about vectors in space. All right, the most basic notion, the example of a vector, is the interval between 2 points in space. Given 2 points, there's a vector which connects them. That vector could measure the, could have to do with how far somebody walked or whatever. That's a vector. It has a direction. It has a magnitude. And if we wanted to, we could think of it as a vector beginning at the origin and ending up someplace else. It doesn't matter where it begins, but the vector, this is the vector. We can move it around. It's the same vector, but we can think of it as being an excursion starting at the origin and ending at some point x. And it has coordinates, in this case x, y, and z, the location of the final point. Or we could call them xi, I being 1, 2, or 3, representing x, y, and z. 3 coordinates. Xi would really stand for x, y, and z. Or x1, x2, and x3. All right. Now we have another added component to worry about. Not only do we want to know where an event is, but we want to know at what time that event is. Let's suppose that we're measuring space and time relative to some origin. That means we have to add in another coordinate, t. In other words, the vector becomes a 4-dimensional object with a time component and space components. The normal notation for it is to represent it 2 different ways. I'll tell you the 2 different ways. We can represent x, y, and z by calling them x mu. Mu goes over the 4 possibilities usually it's normally one arranges them as t, x, y, and z. X mu. And what does mu run over? What are the values of mu? Well, why did you say 0? Because everybody says 0. Yeah. Did you hear me say it? I didn't know I said it. Okay. Right. For whatever reason, historically, t was not considered the first coordinate. X was considered the first coordinate. Y was considered the second and z the third. You might have thought that time should be the fourth component. For whatever historical reason, time was thought of as the 0th component. So this stands for x0, which is time, x1, which is x, x2, which is y, and x3, which is z. What about the space-time distance between these points, the proper time? That's t squared minus x squared, the square of it. Tau squared is t squared minus x squared minus y squared minus z squared. But we can also write it as x naught squared minus x1 squared minus x2 squared and so forth. x2 squared, blah, blah, blah. So that's just notation. It's just a notation. Whenever you see a mu, that means the index runs over the 4 possibilities of space and time. Whenever you see an I, that means the index runs over only space. Okay? I stands for space, and mu stands for space and time. Okay? Just as xi can be thought of as a very primitive version of a vector, not primitive, a very basic version of a vector in space, x mu with 4 components becomes the notion of a fourvector. Just as vectors transform when you rotate coordinates, fourvectors transform when you Lorentz transform the space, when you go from a moving coordinate system to another moving coordinate system, and the x's transform exactly the way the Lorentz transformation tells you they transform. We could rewrite this as x1 is x1 minus v x naught. X prime naught, x naught prime is equal to x naught minus vx1, and so forth. And there's no content to this. It's just a way of organizing the components of a fourvector by calling them all by the same name and giving them an index mu. So we'll use that. We'll use that just to make formulas nice and simple.
So they transform linearly?
Yes, they transform linearly.
Such that they could be, you'd set them up and operate them with a matrix?
Absolutely. Absolutely. You can read off from here a matrix. The matrix would be 1 minus v minus v1. Absolutely. You can think of Lorentz transformations having associated with them matrices, and you could write that x prime is equal to this times x. Matrix times column vector. The components of the column vector would be x's and t's. X's and t's. Yes, you certainly can use matrices, and I advise you to do so, because it's a good thing to do. All right, now, let's talk about some other examples of fourvectors. In particular, instead of talking about the components relative to an origin, let's just take a little interval. Let's just take a little interval. It could be an interval along a trajectory. We could have a trajectory. And we might want to consider along that trajectory a small interval. Now, when you hear small, think calculus. Eventually, we're going to be talking about a little differential displacement along here. All right? For the moment, let's just call it delta instead of d. Right? So this differential element here corresponds to, or a not quite differential yet, some discrete distance, corresponds to a dx mu, or delta x mu. Delta x mu means the change in the coordinates, the change in the four coordinates in going from the tail of the vector to the beginning of the vector, and it's composed out of delta t and delta x, delta y, and delta z. Delta x mu. What I want to do now is to introduce a notion of velocity, four-dimensional velocity, which is a little different than the normal notion of velocity. Velocity, in this case, this could be the trajectory of a particle. Let's take this to be the trajectory of a particle from here to here. And I'm interested in a notion of velocity at a particular instant over here. What do I do? If I were doing ordinary velocity, I would take a little delta x and divide it by a delta t. And then take the limit, and that would define for me ordinary velocity. That velocity has three components: the x component of velocity, the y component of velocity, and the z component of velocity. There is no fourth component of that ordinary velocity. Okay? I'm going to introduce now a notion of four-dimensional velocity, and we're going to do that by taking the delta x mu, and instead of dividing it by delta t, we're going to divide it by the invariant distance between these 2 points. Let's call it delta tau. Delta tau is defined so that its square is equal to delta t squared minus delta xi minus, the sums of the squares of the delta x's. Delta x squared, delta y squared, and delta z squared. In other words, it's the invariant space-time distance between this point and that point. We take the square root of this, and it gives us delta tau, and that is called the four velocity. It's labeled by a u instead of a v, and it has an index mu, so it runs from 0 to 3, 4 components. Now, how does this thing relate to the ordinary velocity? We're getting, we should probably go if we want to get seats, but we'll continue next time. I'll tell you where we're going. We're going toward a theory of the motion of particles. To have a theory of the motion of particles, we have to have notions such as velocity, position, of course, momentum, energy, kinetic energy, whatever. We're moving toward first of all, just the motion of particles, and then toward the dynamics of how particles move. The generalization, if you like, of F equals ma. We'll have a notion of acceleration, all the things that Newton had, except the relativistic generalizations of them. And they will be in terms of Fourvectors. Okay, let's see if we can grab let's see. I have 10 to 8. Who's right? That clock's right. We better get yourself a good seat.
For more, please visit us at stanford.edu.